And welcome back. So the last time we covered the concept of correlation. And if you remember, correlation analysis tells us if two variables are related in some way. And there are different ways that they can be related. We can have a positive relationship where increases in the x variable are associated with increases in the y variable. We can have a negative correlation where increases in the x variable are associated with decreases in the y variable. And of course, there can be no relationship whatsoever, that no matter where you are on the x axis, that tells us nothing about what's going on the y axis. So those are the three types of relationships that we might observe or obtain in correlation analysis. And that's all fine and good, but sometimes we want to do a little bit more with a relationship. Not just whether two variables are related, but once we know they're related, can we use that information in some way to make predictions? For example, if you had no information at all about an individual, other than knowing that they belonged, this individual came from a set of scores that you have, maybe their age, and I asked you, what do you think this person's age is? What would your best guess be? Well, if you had no other information other than knowing that the individual came from some population that has a certain mean, your best guess would be the mean of the population. Why? Well, that's where the majority of people are. So what's your best guess if you don't have any other information? But what if I told you that this individual had graduated from college and had worked his way up in a company that he was working for the last 20 years and was now a vice president? Well, now you've got a little bit more information. For example, he graduated from college, so you can assume that this individual is probably in their early 20s, maybe 22, and has been working for a company for 20 years. So add 20 years to that, that person is sitting somewhere in their 40s. So with a little bit more information, you can make a more accurate prediction about somebody's performance or score or where they belong in some distribution. And that is the purpose of regression. It's to take a correlation and tell us a little bit more and be able to make predictions about a y variable once we know something about x. So what I'd like to do now is walk you through an example of regression analysis. And the analysis that we're going to do is going to look fairly similar, or at least it's going to be an extension of analysis or an exercise that we did back when we talked about correlation. Specifically, we're looking at the relationship between the number of storks in a given geographic region and the number of babies born in that specific region. So I've got those data, the exact same data from that previous example. Down at the bottom, you see I have the mean and standard deviation for the number of storks in those regions, and I have the mean and standard deviation for the number of babies born. So the average number of babies born was 29.833. You see that. And the average number of storks in an area was 20.083. Now, if you remember from our analysis back then, I'll just remind you, the correlation between our x variable and our y variable, between stork population and number of births, was r equals 0.751. So it's a fairly strong positive correlation. You remember what that is? Well, what I've put up on screen here is a scatter plot of those same data. So if you remember a scatter plot, each point on the plot corresponds to each pair of scores from the data. So for example, I will find this score right here, which corresponds to a 15 for the number of storks in an area. And if we look over on the x variable and find a 15, we actually find two of them, but one of them is quite high, and that corresponds to a 33. So that's what each of those points represents. But then look at this line here. I'm going to change the colors. This line is called the line of best fit, or the goodness of fit line. You can hear a couple of different names. And this is the line, I won't go into the technical aspects of it, but it's basically the prediction line that if we ever, once we calculate a correlation and a regression, once we know the number of storks in an area, wherever they fall on this line, if on the x-axis, if we go straight up to where it intersects that line of best fit, and then head over to the y-axis, that tells us what the predicted y-score will be. So that's what regression analysis is all about. It's taking the correlation, calculating this goodness of fit line, and then we can use that formula for a line to predict y once we know x. So what I'm going to do now is show you how to calculate a regression analysis and find that line of best fit. And here is the formula for a regression line. And it may look a little bit familiar to you. At least I hope that it does. Although if you're like me, when you learned it in high school, we had slightly different letters. We once again had y, or in this case, that little symbol up there is called y hat, equals, and the way you and I probably learned it was mx plus b. Okay, and that's the formula for a straight line. In statistics, just because they like to change things up and keep us on our toes, we don't use the mx plus b, we use bx plus a. But those letters stand for the same thing. What are all these points? Well, y hat is the score that we are predicting, okay? Or it's our predicted score, put it that way. And then b, which you guys know as m, most likely, is the slope of the line. In other words, how steep that line is the slope, right? And then there is, of course, x, which is the predictor. I don't know why I'm writing in lowercase. I never write in lowercase. Once we know x, we're trying to predict y. And then lastly, variable a, which is the y-intercept. And the y-intercept is the value of y when x equals 0. In other words, where that regression line crosses the y-axis when x is 0. That's supposed to be x equals 0. Okay, so those are the parts of the equation. Now, how do we calculate it? Normally we know x. That's part of the point, is we measure somebody on variable x and we use that information to predict y. But how do we get b and a? I'm glad you asked. So first what I put up here is the formula for b, for the slope of the line. And I'm actually going to tell you, don't even worry about this part here. I just put up the theoretical formula so you can see what it is. It's called the covariance of xy divided by the variance of x. But don't even worry about that. There's a much simpler version, and that is this part here, which is very simply r, right, the correlation coefficient, times the standard deviation of y, so we're going to calculate the standard deviation of all of the y variables in our data, divided by the standard deviation of x. And you all know how to calculate standard deviations, you know how to calculate r, that's all there is to it for calculating b. And once you have the b variable, we can plug that into a formula for the a, or y-intercept, which is what the next formula that I put up. Once again, very simple to calculate. The y-intercept is calculated by taking the mean of the y group and subtracting the product of b and the mean of the x group. And since we just calculated b up above, we can just plug that in here. You, of course, know how to calculate means. Voila. You do that, you have b, the slope of the line, and a, the intercept of the line. You have everything you need to calculate that line of best fit, or the goodness of fit line. So now let's put this into practice and calculate the regression line for our stork and baby's birthed example data. Okay, so let's clean this up here. So clean things up a little bit. Let's just remind ourselves that the mean of the stork population was 20.083. That's a 3. And with a standard deviation for the storks of 6.775. 6.775. Then, I'll change colors. How about blue? The Y, make it at least look pretty. The mean of the Y group, that is the number of babies born, was 29.833 with a standard deviation of 4.629. Okay. So that's all of the data. We can now plug that into our formulas. So first, let's calculate our B. We need that first before we can even get to A. So B, once again, cross that out, is our correlation. And if you remember, our correlation was 0.751. That was from the last chapter. We're going to multiply that times the standard deviation of Y. Remember, Y goes on top. So that'll be 4.629. There's a point there. Divided by the standard deviation of X, which was 6.775. I just pulled those two numbers there. And when we do that math, our B comes out to be, 0.513. Okay, we now have B, and we can plug that into the A formula. So our A is calculated by taking the mean of Y, which was 29.833, 9.833, minus our B, which was 0.513, times the mean of X, which was 20.083. Oops, it's supposed to be there. All right. And when we do that math, everything comes out to be 19.527. So that is the y-intercept of our data. If X was 0, then we would have a dot at 19.527 on the y axis. So altogether, let me see, I'm going to squeeze it into this corner here. Altogether, our formula is y hat is equal to our b variable, 0.513 times x plus our y-intercept, which was 19.527. And that, ladies and gentlemen, is the regression formula right there. Y hat equals 0.513x times 19.527. I should also mention one thing. In regression analysis, don't get worried about the signs. For example, our B can be negative. If we had a negative correlation, our slope is going to be going down and to the right. And so the slope, our B variable, would be negative. Well, in this case, we had a positive correlation between storks and babies being born, so we have a positive B. But don't get concerned if you get a negative answer, because it's entirely possible if the correlation is negative. So now that we calculated a regression equation, let's take a look at that line of best fit once again. So here's our regression line, and remember that y hat equals 0.513x plus 19.52, I forgot the number, 527. There we go. And how do we plot that line? How do we draw this line into our graph if you have a scatter plot? Well, it's very easy. Here's a couple of points. The line will always, always, always pass through the coordinates mean of x, mean of y. So if you identify where the mean was, and the mean for our stork population was 20.083. So if we find 20.083 on the graph, it's somewhere around there. And the mean of the y group was 29.833, which is going to be somewhere around there. And where those two intersect, bink, bink, my drawing's not perfect. If you just put that dot on your scatter plot, pretend the red line isn't there, that's 1 point. And then all you have to do is make up any point along the x-axis and plug it into our formula. So let's say, for example, you decided to pick a score of 25 for x. Let's put a 25 right there. So if we take 25 and multiply that times 0.513, and then add to that 19.527, we get a value of 32.352. You can try that out on your calculator, but so we now have a score of 25 and a 32.352, maybe somewhere around there. And we're going to see where those points intersect. Looks like about right there. And then all you have to do is connect those two lines and continue on in both ways. And notice that those 2 points form or fall on that line. Well, if you were doing this with a scatter plot, you wouldn't have the line, but you just connect the 2 points and you've drawn it. And now you can have the complete regression equation. Now, anytime you measure the number of storks in a geographic area, plug that into your x on the formula, and you can find out how many births are expected in that area. So that's pretty cool, but, and you knew there was a but coming. How many of you have ever heard somebody try and predict, how many people would vote for so-and-so in an election, or whatever it was you're trying to predict? They're rarely exactly right. And regression is no different. All predictions, all statistics have some degree of error in them. That's why we've been measuring things like standard errors and standard error of the difference and so on and so forth. Well, in regression, we also have some degree of error. We expect to be, or we hope to be, fairly close to the actual y variable, but it's probably not going to be exactly what the real life turns out. But we can calculate how close we expect to be using something similar to the concept of the standard error, and that is called the standard error of estimate. I just cleaned things up and put the formula for the standard error of estimate up on the screen here. Standard error, error, I guess it helps if I could spell, of estimate. What does that mean? The standard error of estimate. Standard, average, right? That's the word that we can substitute in there for a general idea. The average amount of error in our estimate or prediction of y. That's what that formula is going to tell us. On average, how far off should we be when we use the regression formula? So look how we calculate it. Not too hard. Standard deviation of y, which we've already calculated, times the square root of 1 minus r squared. R squared is that coefficient of determination that we learned about in the correlation lecture, times n minus 1 divided by n minus 2. All very straight stuff, very simple stuff. So let's put this together with our stork data. So we had in the stork study, we had an R of 0.751, which means that our R squared was 0.564, right? Just square 0.751. So our standard error of estimate, that's y and x, is the standard deviation of y. And if you look back a couple of minutes in this video, you'll see that was 4.629 times the square root of 1 minus r squared, which we just showed you is 0.564. And that is multiplied by n minus 1. So n is the number of pairs. There were 12 pairs in our data, 12 observations of number of storks in an area, and so on. So 12 minus 1 is 11, and 12 minus 2 is 10, and that is the formula, right? Standard deviation of y, 1 minus r squared, n minus 1 over n minus 2. And when we calculate all of that out, it comes out to be 3.206. That means whenever we plug in a number of storks that we've observed in an area and use that to predict how many babies are going to be born in that area, we will, on average, 68% of the time, be within 3.206 number of births, plus or minus. If we wanted to be 95% accurate, we would do 2 times 3.206, which would be 6.412. So we would be within 6.412 live births, and so on. So hopefully you see the standard error of estimate just tells us how far off our predictions will be. Obviously, we want this number to be as small as possible. If our standard error of estimate was, say, 30 births, then, and the mean for the number of births was 29.833, well, we have hardly any accuracy in our prediction. But with only 3.206 as a standard error of estimate, I'd say we're actually doing pretty good. And of course, the stronger your correlation, the smaller your standard error of estimate will be, because that correlation has a role in the formula. Okay, so those are all of the parts that we've learned about regression. We learned overall the formula, the regression line formula is y hat equals bx plus a, where b is the slope of that regression line, and it's calculated using r and the standard deviation of y over the standard deviation of x. We learned about a, which is the y-intercept of that regression line, calculated with the means of y and the means of x, and b that we just calculated. And then we recognize that there's always a little bit of error in our statistics when we're dealing with samples trying to predict a population. So we learned how to calculate the standard error of estimate, which gives us the average amount that our prediction is going to be off. All right, and that's it. Very straightforward, fairly simple set of calculations, but very powerful in terms of making calculations. And incidentally, I'll just add something more so you know that if we had more variables that correlated with y, for example, not only the number of births in an area, but, the number of storks in an area, but perhaps the average temperature. Maybe that has something to do with babies being born. If it's very cold, a lot of people are inside. What do you do when you're inside? Well, you get the picture. We could add another b to go along with that new variable, and so on, and so on, and so on. And that's called multiple regression. And the more variables, the more predictors that we have, the more accurate our prediction is going to be. For our purposes, we're just going to do calculations with a single x variable, but I want you to know that it can be done with more and more and more, and assuming all of those x variables are correlated with y, our prediction is going to get more and more accurate. And now it's your turn. So I've got some data both on the lecture notes, and then I put the data set up here on the screen. Essentially, this was a correlation analysis, or at least the data that is examining the relationship between depression, in this case scores on the Beck depression inventory, that's our x variable, and a person's self-esteem, measures of how well or how good or positive they feel about themselves. So higher scores on X means more depression. Higher scores on self-esteem mean greater self-esteem. So your job now is to calculate not only, to calculate the correlation between those two variables, and then also the correlation between those two variables, and then conduct a complete regression analysis, including the standard error of estimate. Now, I've already done this in the lecture notes, so you can look ahead and see what the answers are, but I challenge you to do it by hand and then compare your results with what I have in the lecture notes. The table that I have set up has got you started here. You're going to need to calculate your x squareds, your y squareds, and your x times y as you make your way through the correlation formula. And then you'll also, remember, need the mean and the standard deviation of x, and you'll need the mean and the standard deviation of y as you calculate the regression equation. So go ahead and work on that, check your answers out, and if you get that nailed, then you're ready for the homework and ready for the exam. This is not a very difficult concept. Thanks a lot for sitting through it, and let me know if you have any questions. Take care.